The second major topic that we'll discuss today are Markov chain Monte Carlo processes, or MCMC processes. My guess is that most of you have at least heard of that phrase before. Maybe you've read some papers that have used it. And so hopefully those terms are familiar with you, but if not, that's fine. We'll go through them. It's really the main workhorse of Bayesian statistics, as well as kind of lots of other analytical approaches. So learning the details of Markov chain Monte Carlo processes is quite helpful, regardless of if you go on to use Bayesian statistics or not. All right, so let's get started with that. Okay, to start out with, we'll just introduce you to what it is. So what is Markov chain Monte Carlo? What does that mean? So it's really two components. So the Markov chain is one part, and the Monte Carlo part is a different aspect of it. So a Monte Carlo process, it's really just a randomized process. So for example, picking a random number from a list would be considered a Monte Carlo process. So it's really, Monte Carlo just means randomization. And it comes from the name of the Monte Carlo casino in Las Vegas. So any randomized process could be considered a Monte Carlo process. A Markov chain, it's a process where the next step only depends on the current location. And so that's going to make a lot more sense in a minute. So essentially where the chain is going to go next depends on where it is now, or it depends on the conditions of where it is now. And so when you combine these, we're combining randomization processes with a Markov chain process that's going to evaluate some position in the future relative to where it is now. And that might seem very abstract, but we'll start with simple examples, and then we'll get more and more complicated. So a common way to introduce the idea of Markov chain Monte Carlo processes is to think about a robot walking through a field. So let's say we have a robot, and we want that robot to cover every position in a field, but we can only use randomized processes. And so we could set up some sort of instructions for this robot, right? So we could pick a random point along the edge to start the robot. So this is where we put our robot to start this random walk. And then the second step, so then that robot is going to randomly select which direction it turns and then make some evaluation. So if that step will keep the robot in the field, it should take that step in that direction. Otherwise, if that step in that direction will take the robot out of the field, then it doesn't take that step. And so if you repeat steps 2 and 3 enough times, eventually that robot will visit every position in a field, even though it's a completely random process. Right? So let's do some examples of this. So here, the fact that the robot's going to randomly select what direction it turns, then that's the Monte Carlo part, the randomized part. The Markov chain part is this step here. So whether or not the robot's going to take the step depends on the condition of where it is now. So if that step is going to take it out of the field, and that's depending on where it is now, will determine if it takes one step in a certain direction, if that'll take it out of the field. This is the Markov chain part, right? So whether or not it takes that step depends on where it is now. And so again, if we combine these two components, the randomization part with the Markov chain part, eventually the robot's going to visit every position in the field if we give it long enough. Okay, so now let's go through an example. So here I've simulated a field, which is just this box of different x values from -10 to 10 and y values from -10 to 10. So I guess it should be a square, but I made it a rectangle. And so here I've just made a little R script that does this. And so what it's going to do, it starts out with a random position along the edge of this field, and then it just carries out that process. So it randomly selects which direction our algorithm, our robot's going to turn. If that step will keep it within this field, it takes the step. If not, it proposes a new direction to turn, right? So if we go back to this sort of algorithm, if the step would take the robot out of the field, then you just go back to step 2, and you pick a new direction to turn, and then evaluate it. And so you keep on doing steps 2 and 3 for a large number of times. So of course, if we give our robot 100 steps, it's not going to visit every position along this particular field. But each time we run this, it should look differently, right? Because it's a random process. It's going to evaluate different parts of this field each time we run it. So we can do that again. So here it clearly stepped over here and evaluated some spaces over here. We can do it again. Again, it's going to look different. So the path that the robot takes is going to look different every time we run it because it's a random process. And also where it starts is going to be different every time we run it. But again, the more steps we give the robot, the more of this field it's going to cover. So of course it's going to cover some areas a lot and other areas not as much. But if we give it enough time, it should visit every spot. So clearly for this particular case, 1,000 steps isn't enough to visit all of it. But again, we can still look at the random nature, right? So here's one visualization of 1,000 steps. So here's another. It's going to take a different path across this field, and so on. And we can increase the number of steps. So if we give this robot 10,000 steps, it's pretty much going to visit every place in this field. Again, some of these places you can't tell from this visualization, but some of these places it's visited many, many, many times, and there's a couple places it hasn't visited, but it's pretty much covered the whole field with 10,000 steps. Okay, so I want you guys to experiment with this now, but I'll walk through what I want you to do here on my computer, but then you can do this on your own. So I've written a script that does these simulations that I just showed you, and it's a script file called basic-mcmc.r. So you should put that file, you can, download that from Brightspace, put it in R's working directory or set R's working directory to wherever that is. And then to make the functions in this script available to R, you have to source it. And so this, you just use the source command and then put the script in quotes. So this is a little bit differently. So if you've loaded a package into if you've downloaded a package and you want to make those functions in that package available to R, you type library here and then enter the package name. But if you have scripts in an external file, that's called a source file. And then so to make the functions in that source file available to R, you have to use this source command. So that's why it's a little bit different. So you can load this into R, and then, wrong way. And then the function is called basic MCMC, and then the only argument you need to enter now is how many steps, so n steps. So you can set this to different numbers. And just for those of you that don't know, with R, when you hit the up arrow on the command line, it will scroll through the previous commands you entered. So if you don't want to enter this whole thing every time just to change the number or just to run it again to see what it looks like, then you can use the up arrow to scroll through. All right, so I'm going to do this on my computer just to show you how some of this looks. Okay, so here's my R command. So I'm going to, hopefully you can see this. I might move this up a bit. Okay, so I'm going to source basic MCMC.R, and then it was basic MC, I think, and then end steps is 100, and it should do the plot for me. So if we do that, so there's, and this is how it should work on your computer too. And then if I want to do it again, so instead of typing that all out again, I can just use the up arrow and it'll show me that again. So this time it's going to look a little bit different. I can do it again. This time it's going to look different. Again, because it's a randomized process where the robot starts and which direction it turns is different every time. So every time I run this, it's going to be different. It's going to cover different parts of the field. But now I can change it to 1,000 steps. We'll see how that looks. Okay, so it's covering more of the field. And each time I do this, it's going to cover different parts of that field. Its path is going to be different. Now I can change it to 10,000 steps, and this might take a little while. We'll see. Yeah, so 10,000 with 10,000 steps, it seems to cover the whole area. But it's still going to look a little bit different each time. There's going to be a few missing spaces each time, and so on. So anyway, I want you guys to play around with that and just to get a feel for it, and then we'll come back once you're done playing around with it.